Hi, ladies and gentlemen, I'd like to welcome you to this October meeting of the Delaware Astronomical Society. First order of business, any new members that'd like to say hello and say who they are? Let's see if I can point this at you.
Joe DeSanta, and I'm completely new to this, except for spending probably the amount for a small electric car. I know how to set it up, I know how to track, and that's about it. So I'm looking for help eventually, and that's why I like to join.
We'll be glad to help you. Welcome. Welcome.
Oh, I may have neglected to mention earlier tonight, the every other Tuesday that I said is more of a casual hangout.
Right.
One of the objectives is that is we welcome members and non-members to bring equipment out that they need help. You know, pretty much, I mean, I'm not an equipment pro, but a lot of other people are. So if on a non-third Tuesday, any other Tuesday, if you were to come out and bring your gear, there's always going to be a handful of people there that could help you with it. So
Perfect, thanks.
you got it.
Any other new members?
His name is Sam. He's not technically a new member because you all are.
That's all
nice
good.
to him.
By all means. Welcome. Yeah,
Welcome,
by all
Sam.
means. Have fun. Any other new members? I think everybody else is familiar.
And anyone online?
Anyone online? I'm gonna try and set this back up here.
Yeah.
Yes.
My name's Stuart Levin. John Conrad's a friend of mine, and I like listening to his talks, and thought this one would just be another great talk. So
Fantastic.
I'm interested. I'd seriously consider joining.
Great. Welcome,
Excellent.
Stuart.
Welcome. All right, so next item on the agenda, Lynn, did you want to say anything about the calendars or anything? We're all good with that? Okay, very
I
good.
will email those who are not here so that we can get together and pick them up.
Very good. All right, next item. Bob, do you want to talk really quickly about treasury stuff and the dues?
Yeah, we're beginning the 2022 dues renewal process. The dues for next year will remain the same, $30 a person for the year. And this week I'll be sending out an email that to the current members that that gives you options to pay. This year, I guess we'll have some in-person options. You know, either at the Tuesday workshops or at the meetings. You know, you can give the money to any board member. So we have in-person options, but then there's also the email will have a link with a PayPal that you can pay by PayPal, or just if you want to use your own PayPal account, you can send the money to dos@mountcube@gmail.com, which is our PayPal account, or you can mail a check to me. So the email will have all that information. So again, it's the dues for next year, $30. We'll be doing this for a while. I think the focus will also have links to and also our website has, if you go to the new member area, you can just sign up there as a new member, and it has all the links there too. So there's a lot of different ways you can pay.
Very good. Real quick, can you also tell us about the book club meeting?
Okay, yeah, the DOS has a book club. They meet every month, typically the last Thursday of the month at 7 o'clock. They're still meeting over Zoom, so you have to get the Zoom link. So this month's book, this month's meeting is at October 28th at 7 p.m. And this month's book is Miss Levitt's Stars by George Johnson. It's a fairly thin book, pretty easy read. So if you're interested in attending that, you read the book and attend. If you want to attend, send an email to DOS Book Club, all one word, @gmail.com. That way you can get the Zoom link for the meeting. Also, the club calendar on our website should have the meeting notice in there for the book club meetings, and should have a link that you could get the Zoom link from there too. So
very good. And Bill, can you tell us about the AP SIG?
Sure. The Astrophotography Special Interest Group will meet in November, again over Zoom, and that'll be on November 20th. So the pre-announcement goes out to the groups.io, the DAS at groups.io, and we'll also go to APSIG members by direct email. That's about it?
Oh, and Bill, that's a great segue. I always forget, since we talked about new members, we always highly recommend that any new member join, well, old members as well. The club uses a groups.io for its email conversation. We used to use Yahoo groups that went defunct. It's now groups.io. There's information on how to join both on the website as well as in the Focus newsletter. Again, it's really the way that we stay in touch in between meetings. You'll see people asking questions about how to use equipment or what equipment to purchase. You'll also see announcements about some impromptu dark sky observing sessions, announcements about the book club, and some of the other special interest groups, the AP SIG. So again, highly recommend that people join the groups.io. And again, if there's, it's very simple. It probably takes 2 minutes, and there's information out there for how to do so. And if you need help, just again, reach out to somebody.
Very good. And I'd also like to thank Jeff. He ran the board meeting for me a few minutes ago because I was late to the meeting due to attending a conference. It was pre-scheduled, so we had arranged it ahead of time. But we had a really full agenda and a really cool plan that we set forth so that we can get a move on all these projects that we were planning to do before coronavirus hit. So we want to get them all going off the ground again. And so we did quite a lot during that meeting, quite a lot of planning, and people volunteered to do stuff. And we're really moving forward with a whole bunch of projects. Jeff, you want to summarize?
Yeah, basically, we're just trying, the best way to sum it up is we're trying to get the Solwyn, the DAS pod, and our equipment loaner programs really spiffed up and polished up and ready as people are starting to gather more and more these days. The refractor, 6-inch Apo refractor that the club bought a bit before the pandemic is now mounted and installed in the pod, and it's got power running to it. However, since we've installed it, there's not been one clear night that we've been out here, so it hasn't been aligned yet. But Bill Hannigan is going to be taking over, the last couple of steps to get that really ready, usable, and with a set of instructions so that we can start getting people trained on how to use it. We're looking to increase our club telescope loaner program. We've historically had a lot of Dobbs, but we're looking to supplement that with refractors as well as SCTs. So again, a lot of good stuff happening. It's kind of a nice tie into the announcement about the dues because, the dues do go to good uses, and we always try to find ways to make sure that the club is serving its members as best that it can. So again, a lot more announcements to come on that, but we are looking to really make some good advancements on all of our equipment. So.
Yep. Yeah, we ran out of time a little bit during the board meeting there. We had a lot to do, but we got a good start on it, I would say.
Yeah.
And so I think things should go well. Going
The
forward.
main one along those lines is, as I mentioned, one of the things that the club has historically not had loaner SCTs. The club currently has 3 of them, and we're looking for somebody that is probably knowledgeable about SCTs to kind of lead the charge to assessing them, fixing them up if relevant, making some recommendations. My opinion is, of the 3 SCTs, we really only need 1 loaner. So someone that could assess and make some recommendations about maybe which one that is. Again, if there's someone that's knowledgeable about SCTs and would like to help the club, again, please reach out to me or Rob or Chris after the meeting. We can give you more details.
And the good news is we've actually already started this process.
Yeah.
We've started repairing them. We started to analyze them, but we really need someone to take up the charge of finishing that project because we don't have time for it. So somebody would be great to do that. If someone would be an awesome member and volunteer their time, we would really appreciate it.
What's an SUP?
Oh,
SCT, Schmidt-Cassegrain Telescope.
a folded optics telescope. Yeah.
That is a good question because we're saying that to everybody.
Yeah.
So we should probably say what it is.
Yeah, that's true.
Anyways.
Well, if you didn't, you know how to assess.
Yes.
That's why I didn't ask.
I'm gonna
If you
say-
don't know what one is, you're probably not the right man for the job.
That's right.
But it's a fair
That's why I
question.
didn't ask. It's a fair question. I can't help it.
That's not gonna stay.
I think it's maybe
If the
tension.
cord is too tight, yeah. We can move that over a little.
There you go.
Sorry, guys.
SCTs donated?
Yeah,
Okay.
I believe all 3 of them were donated
They were.
over the past couple of years.
Yep, all 3 of them were donated at different times.
We've got
Mhm.
2 8-inches and 1 10-inch in all various states that, again, I can get into more detail later about.
Yes, none of the three are actually ready to loan right now,
Yeah.
but we need to get one ready to loan.
I think the students ready to go.
Cool.
All right, so anyone else with announcements that we missed? We good?
Just the general comment,
We
again,
continue.
we're still kind of in the same holding pattern, all DAS events at this point. Well, the main meetings and the Tuesday
Jeff, you wanna come up
workshops.
and say that?
Oh, sure.
Up here, so you can see. Where they can see.
Our main meetings as well as our Tuesday workshop meetings will continue to be hybrid. So people are welcome to come to Mount Cuba if they want to be here in person. If people are more comfortable to be remote, we will continue to tie them in via Zoom. Again, for the foreseeable future. The other special interest groups, it looks like they're all handling it different ways, but just, biggest thing to let you know is people are welcome to come up to Mount Cuba these days. But we are still trying to accommodate the people that are more comfortable staying home with the Zoom for now. So business as usual. We're really not. We are holding member star parties and they have been happening because that's relatively safe and easy to keep distance, but we're not really encouraging outreach programs. That being said, we've been having some discussions about maybe some ways that we could do some creative outreach that doesn't involve lots of people smashed together and little kids and unvaccinated people and all that kind of stuff. Anyhow, there's not been any outreach activities, not to say that there couldn't be, but we're not pushing it at this point. I think that covers it. So without further ado, Rob, is sharing enabled?
You click right there on security. And click up there and share.
No, because John needs to share his screen. Is that what allow participants to share screen? Okay.
There you go.
Okay, so on to tonight's program. And actually, after I finish making this announcement, I will rotate the webcam around so you get to see the broad audience. We are welcoming back tonight John Conrad, our NASA ambassador. And John, is your internet is your internet more stable now?
I seem to be solid. Do I sound
Okay.
good?
You sound great. Yeah, give me 1 second. Let me get the webcam adjusted and let you take it away, maybe.
There you go.
Hey, we got most of you in there. All right, how's that look, John?
Fantastic.
We got about 20 of us here in person, and it looks like another 10 or 15 virtual. So we got a good crowd. Again, John Conrad, our NASA ambassador, joining us via Zoom. We're always glad to have him, keeping us up to date with what NASA is up to. John, I believe you should be able to share. Take it away.
Great. I'll just say a couple of minutes to all of you assembled folks and my thumbnails here on the screen. It's great to see you. And I imagine maybe especially some of the ones in the small thumbnails by themselves feel the same way that I do, which is out of an abundance of caution, if you've ever heard that. I'm here and you're there. And boy, do I look forward to sort of wandering around at the front of the room there again. And so hopefully the next time I give a talk, we'll be doing that. But it's good to see you all, and we'll get on with it here. I'll share my screen. And let's see if you can see that.
Oh, let me just do one last little thing. Oh, and I'm sorry, my usual, gosh, I'm so out of practice here. The usual routine for those on Zoom, we are going to mute you all and then unmute John, because I'm not going to be sitting right at the computer. Rather than using the chat for questions, we'll just have people unmute themselves temporarily. And John, what's your feeling on questions? Do you want to wait or just have them come as they come?
Come as they come is just fine.
Okay,
Just
very
fine.
good. But for now, I will be muting everybody.
Click participants.
Thank you, Rob.
See participants. So click the icon. And you want to click at the bottom.
Mute all.
Yeah. And you have to
And then we'll unmute John. What? Oh, ask to unmute. Okay, that's right. We can't unmute somebody. John, go ahead and unmute yourself and you should be good to go. Which I'm not sure he can hear me.
Can you hear me now?
Yeah.
Good.
You sure? Because I got things flashing on the screens. You hear me talking?
Yes.
Yeah.
Great. And you can see my slide.
Yep.
Yes.
All right, here we go.
And you can hear us, right, John?
I sure can.
Okay, cool.
Yeah, I moved to a different room of the house so that I'm literally 5 feet away from the router instead of, whatever it was, 60 feet away or something. It's great to be back to talk to you guys. I wish I could say I have an exciting new mission to tell you about, but somebody's stolen my headline lately. Somebody named NASA, and not only have they talked a lot about Lucy, but they've actually launched it. So here we go with the look at NASA's not next great spacecraft, but the one that they've got up there now. And it's we're first going to talk about where it got its name. But before we get to that, I want to talk about a guy who's really quite remarkable. And he's the PI for this mission, Hal Levison. He's a PhD. He's probably almost a contemporary of mine, so he's been around a while. He's been around Lucy for more than a dozen years. It's been in preparation. He's been involved in many other programs as well. But the reason I wanted to get his name out there is an awful lot of the slides you're going to see were straight from his presentations. He's talked to us 3 times in the last couple of years. He's head of the mission that launched this week. So he's been a really busy guy, and yet he and I have exchanged emails on a couple questions I had within the last week and a half or so. So he's very approachable and really, really good guy. You'll probably see his name in the press a lot now. Down in the lower right-hand corner there, I wanted to give credit to the NASA organization that's managing this. That's NASA Goddard this time. And so you often hear JPL for the deep space things, but Goddard down in Maryland is another center. It's one that I actually worked for several years, leading studies for them out of GE Aerospace. And they are the owners, if you will, of managing this particular mission. SWRI, you may or may not know, they really have been quite accomplished. Not as much as JPL, who've done more deep space missions probably than anybody by far, but SWRI, Southwest Research Institute out of San Antonio, and APL that you see there, Applied Physics Labs out of Johns Hopkins, they also have managed a fair number of missions. SWRI also has New Horizons, for example, and also Juno at Jupiter right now. And the other logos you see, Lockheed Martin is the spacecraft contractor. That's my alma mater. And APL, ASU, Arizona State, and Kinetics are 3 instrument contractors. So let's get on with Lucy and understand why it's called that. You've probably seen this, if you will, arrangement of bones and logo that's been used now for decades to represent some of the earliest human fossils that we have found. An archaeologist named Donald Johansen in Ethiopia, his team discovered this particular one, and I'm going to try to get the name right. Australopithecus, I think is what it's called. And I believe it was the first one that was found. 40% of the bones of this lady were located, and she's become quite famous. You'll see this particular set of bones in many places, but the point here is she's a human ancestor fossil, and Lucy the spacecraft took the name because she's going to go visit some fossils in the solar system. So a couple of quick interesting stories may have been in the news lately as well. Donald Johansen and his team back in the 70s loved listening to the Beatles. They were playing Lucy in the Sky with Diamonds a lot when they discovered this and dug it up. And so he chose to give that name to the fossil. And NASA in turn was inspired to take the diamonds part and turn that into the shape of their logo. So there you have it. All right, so fossils in the solar system. Let's think about that for a second. Basically, fossils are the earliest progenitors or primordial physical evidence of something. And in the case of the solar system, where we see this artist concept, since we don't get a selfie of this, of the actual formation of the solar system, you see that the sun is lit up in the center and that all of that mass of gas and dust has spun into a flat disk and is spinning, and these spinning objects start to clump together into what we think of as just grains of sand, which is a process we don't really understand very well. But then the grains, due to gravity, clump together into planetesimals, and the planetesimals can be a variety of sizes from very small to quite large. The largest planetesimals we know are, asteroids of a variety of sizes as well. And once the planetesimals in a particular lane out from the star, in this case the sun, start being pulled together increasingly and smashing together, and eventually lots of heat and lots of mass is collected and compressed, and we end up with a hydrostatic equilibrium of this large mass that forms into a spherical orb, and you see these planets there in some of the lanes that are being cleared, where they're literally sweeping out virtually everything in their lane in the way of gas and dust and planetesimals. So a long way of saying that there are processes that form the planets. There are processes that form the smaller things like the asteroids and the comets, and yet some of the material remains in its original form and hasn't gone through collisions and changes. And so more and more we're trying to find the earliest material, the real fossils. And so we can better understand the processes that formed everything larger than that, including Earth and the planets. Another artist concept of the solar system shows us looking down on the sun in the center with 1, 2, 3, 4, Mercury, Venus, Earth, and Mars orbits shown there. And you guys already know what that mass of objects beyond Mars is, because before you get to the orbit of Jupiter, you have this mass of asteroids known as the main belt. And so the main belt asteroids and all the smaller material that still hasn't formed into large objects there is indeed a lot of the fossils of the inner solar system. And so I want to think about what's at various places in the solar system and where these fossils, including the ones I just showed you, but also some others, are located. And to do this, we're going to look at this simple graph where along the horizontal axis, the x-axis, we've just simply got distance out from the sun from the lower left-hand corner, 0 distance out to 1. And that's 1 astronomical unit, which, as you're probably aware, is the definition of the distance from the Earth to the sun. And you go out to 10, and you've pulled in the distance out to Mars and Jupiter and Saturn. And beyond that, we have more of the giants. And so we're going to be looking at what's in that particular section of the solar system, the inner solar system, out to 100 astronomical units. And on the vertical axis, we're going to be looking at the shape of the orbit. You remember that Kepler's laws tell us that all planetary orbits are elliptical. And an ellipse can be, in the case of 0 eccentricity, a perfect circle, but most orbits are something out of circular and they have some eccentricity, some squished, some ovalness to them. And so an example is if we do have a perfectly circular orbit and it's close to the sun, it would be down there in the lower left-hand corner. And so let's look at the actual objects in the solar system. And here are the 8 orbs that are our planets as we go out from the inner 4, the terrestrial planets, to the giants. And you see that most of them are quite close to circular orbits. Those that are a little further out, a little more elliptical, are Mars and Mercury in particular. But none of these are oval enough orbits that they actually cross the orbit of an adjacent planet. So there are the planets. And where are the fossils? Well, here they are in the inner solar system. These are the small solar system bodies. That's the official IAU definition or designation for everything other than a planet or a dwarf planet. The dwarf planets you can see as those round orbs out towards the right there. And so you folks all recognize that the colored things furthest in there, kind of the turquoise, are the main belt asteroids. And beyond that, you've probably already identified that beyond the orbit of the planets, what's known as trans-Neptunian objects are beyond the planets, and that's where the Kuiper belt is. And as you move beyond the Kuiper belt, which is by definition only out to 50 astronomical units, you move to many, many more eccentric orbits, which when you picture being very eccentric, they go from way outside deep into space, like the distance beyond the Kuiper belt, in very elliptical orbits that swoop around the sun. And so this is the home or the reservoir of many of the comets. So there's one set of colored small solar system bodies we haven't talked about, and that's the ones we're going to talk about today, the Trojans. And so you see them there at the same distance from the sun as Jupiter, because they are co-orbiting with Jupiter, as you'll see in a minute.
Hey, John,
Yes.
the diameter of the circles, is that roughly the size of the object?
No.
Oh, okay.
No, I mean, if you
Yeah.
know the size of Jupiter and you know the size of Earth, no.
Yeah, I mean, Jupiter's bigger than Earth, but not proportionately.
It's much bigger, much bigger than Earth, than it's shown here. Yeah.
But what is the diameter? Is it arbitrary?
I don't know. It's again one of Hal's. Nobody asked that question, and I didn't think to ask it.
No problem.
Yeah, I mean, Jupiter, just to kind of think of how big it is, when the sun had formed and taken up literally most of that gas cloud that collapsed into a disk, what was left of the gas cloud, most of that collapsed into Jupiter, and on down from there. I mean, it's really something how big it is.
Yeah.
All right, so that's a look at the small solar system bodies and where their orbits are and how elliptical they are. These are the reservoirs that we're looking for when we think about understanding planet formation better, because they're relatively untouched compared to the planets who've gone through violent change and collisions and so on. All right, so we have in fact visited lots of fossils. Here are the spacecraft. They're not all NASA. You see Hayabusa and Hayabusa 2, very successful Japanese spacecraft that had visited asteroids. And in fact, I believe Hayabusa 2 was the one that sampled material from the surface and delivered it back to Earth. I'm going to say, seems to me it was 4 or 5 years ago. One of the other visitors to the asteroids is OSIRIS-REx, which was in the news last year, a NASA spacecraft. The arrow points to the location where it went to either do a flyby or go into orbit, or in some cases actually go down to the surface. And OSIRIS-REx, you may remember, orbited for a while, picked out a landing site after identifying candidates, and then went down and sampled material on the surface, tucked it away and headed for home, and it's en route back to Earth right now. You see also that it is at the same distance out from the sun, 1 astronomical unit, as Earth is. And so that's not just a main belt. It is not a main belt asteroid. It's a near Earth asteroid. The dotted lines show what the origin of things visited was, if they've moved from there. And so you get to see another number of asteroids that have moved out of the main belt, because there are many, many collisions in the main belt between these objects of various sizes. And one of the things that happens in a collision is you lose energy. And if you lose enough energy in your orbit, then you essentially deorbit into a closer orbit to the sun. All right, towards the top, you see some spacecraft, and one of those, Chang'e, is a Chinese spacecraft that have visited comets. And you can see by the dashed lines from there that they came, as I mentioned, from the very elliptical orbits out in the scattered disk beyond the Kuiper belt and headed in towards the sun, and we met them on their way. So that still leaves the Trojans. And so here we have, finally, Lucy's mission. And so Lucy is headed for the last remaining, if you will, reservoir of relatively untouched material in the solar system. And we want to understand that to better understand Earth's formation. So I thought it would be useful to understand where where the Trojan asteroids came from. And so this is a very, very simplistic animation that you're about to see. You see from the left, we've got the sun. We skip the inner 4 planets. We show Jupiter at 5 AU, then Saturn, then Neptune, and then Uranus. And those of you that understand the order of things know that that's not the order of the outer 4 planets. And that's right. This is what the NICE model, NICE, you see it there, has come up with as a view of what took place in the very early time of the solar system's formation to get the planets into the orbits that we see them today, and what happened to all the material that was lying beyond the planets originally, beyond 15 AU here, innumerable objects of various sizes in a very much colder region of the solar system. And so the NICE model ran many simulations and came up with one preferred simulation. This happened, I'm going to say 2004-ish, and it was published in 2005. And one of the 3 authors, 2 of them were Europeans, I think. The other one was Hal Levison, the PI for this NASA mission. And so I was really delighted to hear that when he talked to us about this, because I've seen various simulations from the NICE model many times, and it has stood up for over 15 years now as the, if you will, theory of choice for how the solar system formed. So I've talked long enough. I'm going to show you the simulation here very quickly. You see the 2 outer, what are called ice giants, moving from their positions very early in the solar system's formation, further out, where Neptune ends up all the way out at about 30 AU, and close to 20 is Uranus. And I'm going to not count on you having memorized that. I'll show it to you again here. And so we'll take a look at that and watch what happens as Neptune moves inward and is repelled by the gravitational impact of the inner solar system bodies, which then move themselves. That's not shown in the animation, but they push the outer 2 back out, and Neptune is pushed so hard that it goes past Uranus, and the outer 2 scatter all of that very cold material. and they actually scatter most of it out of the solar system, not just to further distances away, but into interstellar space. Some of it goes beyond and ends up as the Kuiper belt and the scattered disk. But some of it, you may have noticed, was knocked inwards and drawn in by Saturn and Jupiter and ended up trapped at the same orbit as Jupiter's. And you see those objects over there on the left. So that's what we believe is the reservoir beyond 15 AU that was the material that eventually was pulled into 5 AU where Jupiter is. So it came in from a much different region of the solar system than where the main belt asteroids were formed, with much more rocky material in the inner solar system. So here finally then is a simple animation, but a fairly accurate one of the Trojan asteroids in the same orbit as Jupiter. Jupiter is the orange planet. The main belt asteroids are completely left out of this, so we don't confuse the view. And you see then Mars and Earth, Venus and Mercury with their orbits shown accurately in terms of timing. The timing of the Jupiter, of the planet Jupiter, and therefore these trapped asteroids, the Trojans, is about 12 years. And so you're going to see us take advantage of that time as we show you what Lucy is going to do. So what are they doing? Why are they trapped there? Well, you may remember we've talked before about the Lagrange points, which are simply mathematical solutions in the field of astrodynamics to a classical problem known as the three-body problem. And so as the math and astronomy kind of developed hand in hand with people like Kepler and Newton in particular developing a lot of that, one of the questions that was asked was, if you have two bodies that are significant attractors, one smaller than the other, and in this case, we're talking about the sun and one of the planets, are there places in the space near the planet or the sun that are places of equal attraction of the planet as it goes around the sun and the sun itself? And a mathematician named Lagrange in the 18th century came up with a special case solution known as the Lagrange points. He identified the 5 specific cases where the gravitational attraction creates an area of stability where if you put something there, it tends to stay there. L2, you may remember, beyond Earth, if this were the Sun-Earth system, is where we've already put some spacecraft, but which is where we're going to put the James Webb Space Telescope. The 3, L1, L2, and L3 are known as the collinear ones for obvious reasons. The L4 and L5 are known as the equilateral solutions, and they are, by mathematical definition, 60 degrees behind and 60 degrees ahead of the orbiting attractor, in this case, today's case, the planet Jupiter. So let's take a look at that again and note that we have Jupiter and the sun, and 60 degrees ahead is one swarm and 60 degrees behind is another swarm. And they're known as the L5 and L4. The L4 are the leading ones and the L5 following. And because of where they came from, the cold region beyond the original planets, they are different kinds of material, lower density and more volatile rich than we have inside the in the main belt. And so we expect to find interesting things with that. And we've looked at it, we've looked at these Trojans enough times with Hubble and other very large telescopes that we have been able to get a count and to actually view quite a number of them. The count, believe it or not, is about 600,000 Trojans in each of the swarms, so over 1 million of these. And you can imagine that the main belt is much, much more numerous than that. And you see it as the kind of green cloud in this little figure. But there are an awful lot of Trojans out there too. And we've studied them enough to know that they're not a homogeneous population. For starters, of the typical spectral types, in other words, from gray to red of asteroids, where the main belt has about 3/4 that are C-type or very gray, those are the unusual ones in the Trojans. They're about 7% C-type, gray type. They're about half of the remaining 93% for the P-type, which are between gray and red. I guess you can call them pink. Maybe that's where P came from. And finally, the red ones, D-types, are indeed redder to the eye than Mars is. And so those are the 3 major spectral types, and there's quite a range of them across the range of sizes of Trojans. Another way that we have diversity and inhomogeneity is in the reflections. And so whereas you've gotten to know the reflectance of the moon, the albedo, which is quite bright, and Jupiter, Venus, Mars, and Saturn, fortunately, are quite bright in terms of albedo. The percent of light reflected by the Trojans does have a very wide span, but the entire span is below 15%. 15% visible albedo is about the same as asphalt. And so we have a range of very dark to much darker that we're going to be looking for as Lucy gets out there and tries to find the specific target asteroids and then lock on, if you will, to the centroid so that they can take measurements and images and so forth. So it's going to be quite an interesting challenge to make sure that they see them well and identify them early. All right, so we're finally going to take a look at the orbit that Lucy will fly in order to get there. The date you see here of October 17th, as you're probably now well aware, is not correct. That was last Sunday. We actually successfully launched it from the Cape on Saturday morning, which was when the launch window opened. But the people that put together this particular animation to show the trajectory had to pick a date, and they just picked October 17th rather than 16th, and there's not much difference, of course. On the right there, you see an Atlas booster. I like to mention the Atlas because I've got a little bit of history with it personally. You may remember that the Atlas came along early in the Cold War as an early attempt to have an intercontinental ballistic missile. The Air Force, which was very young at the age of about 5 in the early 50s, was given the task, and they developed the Atlas ICBM. But during the 50s, it was recognized that it was a powerful enough rocket that we could also use it to launch payloads into space, even though we hadn't been into space yet. And through the 60s, it became more and more used, what was called SLIC-3, SLV-3, Space Launch Vehicle 3 was the designation for it. And I actually launched a combination of an SLV-3 and an upper stage you've never heard of from Vandenberg in 1968. So they go back a long way. There have been hundreds and hundreds of them. They have, as most of the rockets, become very, very reliable and successful. We're down to our last few at this point. And this is one of the smaller ones. And the reason for that partly is because Lucy had a limited budget. NASA has a program called Discovery, which limits the development of everything other than the launch vehicle to $500 million. and then you can't exceed more than $1 billion for the total mission. That, believe it or not, is on the more affordable side of deep space missions, and that's exactly where Lucy is. And so they're using this rocket in order to get into first low Earth orbit and then into the orbit that you'll see in a second that will take advantage of Earth's gravity assist to finally get it out there. So it's going to take a while to get out to Jupiter, and we are, as I said, underway. And so let's take a look at the first step off of Earth, where you see Lucy and Earth together there in this picture. And so the first thing that happens after launch is we've put Lucy into an orbit around the sun, not around Earth, but around the sun, where it's the same distance out, but it's slightly eccentric, so that it will come back to the sun in such a way that it gets a boost from Earth's gravity about 1 year from now. And the way that works is simply gravity is a wonderful thing, and the potential for it of it in masses as large as the Earth gives you something that you can literally steal if you have the right approach and departure from it. And so the Earth actually would slow down a little bit because of the energy that's taken away as Lucy goes by, but I defy you to notice it. At any rate, so after a 1 year orbit, we get gravity assist, and we go into the boosted orbit, which this time, as you watch Earth go around twice, is a 2 Earth year orbit. And we go by Earth again and get yet another gravity assist. And this gravity assist now gives us enough energy to head out from the perihelion, the closest distance to the sun of this orbit, as it leaves Earth's orbit and heads out towards Jupiter's, which will be the aphelion, or furthest distance from the sun. And so here we go on that ellipse. And the first thing we do is cross through the main belt. Now, that's not the mission of Lucy, but they decided some years back that since they're going through it, why not test the instruments? So there's a main belt asteroid that they've targeted to test the pointing and the instruments on as they go by. And not surprisingly, they decided, since it had some boring numerical name, to give it a name. And the name they gave it in 2015, after they designed this trajectory, is the name of the discoverer of the Lucy fossil, Donald Johanson. So they go by Donald Johanson in what is that, 2025, 3.5 years from now, on the way out. And so here they're going out finally in that Lucy trajectory that will reach the orbit of Jupiter and have its first contact with one of the Trojan asteroids. And the target is this C-type gray asteroid. And this one turned out, they discovered recently, to be kind of neat because it has its own little moon. You see the green orbit there of Quetta going around Euripides. So that was kind of an unexpected bonus after they targeted this. That's going to take place a little less than 6 years from now. 3 years for the first 2 Earth gravity assists and 3 years on the outbound leg of the ellipse. So we continue on and shortly get to the second target, Polymele, a different spectral type, and continue on and shortly get to a third one, Lucas. In this case, this is one of the red ones. And then we have yet a fourth contact in the leading swarm known as the L4 Trojan swarm. And so now you've had 1, 2, 3, 4 targets and a moon, and you've done that all in 15 months, starting about 6 years from now. And now, as you can see, we've passed through the furthest distance from the sun, the aphelion, and we're headed back towards Earth's orbit. And it comes back in and takes the other half of the 6-year orbit, 3 more years, and goes around and gets a little bit of a shift in its orbit, where you'll notice that the major axis, which is just the straight line through these ellipses, is rotated by its passage by the Earth so that you have the proper trajectory to intercept the following swarm, which is known as the L5 swarm. And the target that we have in the L5 swarm is two very special and large asteroids, which we'll talk more about in a minute, Patroclus and Menecius, both the P-type, the pinkish ones. And so the initial mission of Lucy, what you call the primary mission, has been achieved at this point. 1.5 full orbits out to Jupiter, and 4 + 2 or 6 main target asteroids have been found or have been studied as we've done this in a 12-year period from right about now. After that, there is no friction in space. There's nothing to keep an orbit from changing as it that won't in this case, unless there happens to be some major perturbation, like a large body flying very near to the spacecraft, but nothing that you would ever predict or expect. And so you're going to have this particular orbit just continue on, 6-year orbit, as you see here in this animation, where the red thing, of course, is Lucy, out to Jupiter, back into Earth's orbit, back out. And so a 3-year outbound leg, which you, after a while, can note reaches the front end of the leading swarm. So here it'll come now, watch the front end. And the swarm is actually going faster than Lucy is. There's a what's called encounter velocity that I'll talk about in a second, relative to the objects. But you can kind of picture that Lucy as a spacecraft is sort of backing through these faster moving asteroids. And it reaches the tail end of the following swarm and the front end of the leading swarm, and thereby the 6-year Lucy orbit and the 12-year Trojan orbits, where they're only spaced, 60 and 60, works out very well for being able to sample asteroids. And this, they've done simulations on it, will go on pretty much exactly like this for 100,000 years. They've actually simulated. That's I'm sorry, did somebody have something to say?
Oh, just some chuckles on this end, John.
Okay.
What's the power source?
I'm going to show you that in a minute. Let me talk just a second about that encounter velocity. Because I just asked, I asked Hal Levison about that a couple weeks ago. And I was a little surprised, but at any rate, it's 7.5 kilometers per second. And if you think about that, that sounds a little bit fast. You're zipping by something. It turns out when New Horizons went by Pluto, it went by at about twice that speed. So with the way we're able to, aim and lock and stabilize our spacecraft and the instruments, we can get a heck of a lot of data, even though for the 2 largest of the targets, we're only going to be spending 10 seconds in one case and 20 seconds in another case, literally at closest approach. Now, by looking ahead before you get there, by looking back after the, in this case, you're actually looking back as it approaches because the asteroids are coming at you. And then you look at it as it passes by after you've sort of backed past it. You get, many minutes of data in each of these, even though the encounter velocity is very rapid. But for the entire 6 asteroid encounters over a 12-year period, Hal said they're going to have a grand total of about, I'm gonna say 24 hours of data. And I'm going to check that. I may remember that wrong, but it's not a lot of data gathering for a 12-year period. All right, so you've stared at that long enough. We're going to summarize some things about what we're going to have in the way of studied targets. We've got these 4 that I mentioned from swarm, the leading swarm L4, that span the spectral types in only the first 15 months of encounter. And then years later, we get back and we get to the L5 swarm. And so in these 2 encounters, we see the little tiny moon Quetta plus the 6 target asteroids. We cover both swarms and we cover all spectral types. We want to mention just a few things that are really important to understand a little bit so you know why we pick these targets. Euripides is a gray asteroid, much more typical of what you find in the main belt, which makes it pretty unusual. It's that 7%. In the case of Euripides, it's very unusual. It's unique, actually, as far as those that we've observed in the Trojans. And it's unique in the sense that it's one of an identified family. A family of asteroids, if you picture in the main belt, where there are countless families, is the result of some collision in the past that after the dust settled, literally, and the pieces sorted out, they're all in pretty much, they're all flying in a formation due to the fact that they've sort of equalized each other. They were once a larger body, and now they are a number of bodies going along in formation. So they're known as collisional families. A disruptive collision is something that may only happen once a year for large bodies, we estimate, in the main belt. But when you've had an asteroid belt around for 4.5 billion years, that's a lot of collisions. And so there have been many less collisions, apparently, in the Trojans. Not only did they start a little later than the main asteroid belt, but the swarms are much less dense than they are in the asteroid belt. And so far, we have identified only 1 family indicating a past disruptive collision, and the largest object in it is Euripides. And we picked that because we know that it's a broken part of something that used to be bigger, and therefore by studying its surface, we're going to be able to learn things about a change in a surface in the Trojans. Pretty interesting object. There's a lot of diversity in terms of the mass of objects that we're studying. Polymele is very small, 160 times smaller than Patroclus, and Patroclus is in fact the 2nd largest asteroid in all of the Trojans that we've been able to identify so far. Menetius is just slightly smaller. And so there's a very large variance in the masses, and that may be of use in our studies. We're going to look further at this particular pair because they're a very unique pair in terms of what we've found so far in the Trojans, but there's a part of the solar system where these pairs are very common. The name of this is simply an equal mass binary. And you astronomy folks understand what that means. You know what binaries are. In this case, the period of rotation is 4.3 days. And you see the sizes there of these squashed, these ellipsoids, if you will. So the larger of them, Patroclus at about 130 kilometers, gives you quite a nice large target. And so you get about 20 seconds as you pass it at 7.5 kilometers per second. But at any rate, you see a Hubble image showing the 2 there. There have been many images taken of it that have given us the elements of this rotation. And this particular binary, as I said, is very rare in the Trojans, and we don't see them in the main belt, but they are very common in the furthest reaches of the Kuiper belt, and they're known as cold classical KBOs. cold classical Kuiper belt objects. And there are lots and lots of them. And you see images of several. You see an old friend that you may remember there in the lower right, that's Arrokoth, which is not in fact a true binary. It's an almost binary. It's a contact binary. But the others are, rotating around their center. And the fact is that there are many of them way out there, and we believe that they represent a class of objects that are pretty much the most untouched, at least in that region going that far out in the solar system, the most primordial of the planetesimals, and therefore the most interesting of the fossils. We don't really understand, what they are and how they got that way. I didn't actually look into, and therefore I can't really even answer questions about when they say classical ideas don't work. So I don't understand this, but it is a subject of intense study. Here, if you note the date, is a presentation only 2 weeks ago at the American Astronomical Society meeting of a primordial near equal mass binary pair that are closer together than any that had been found so far in the Kuiper belt, and were just reported on, known as JY31. And so it's, as I said, they're very interesting objects, and we want to see if we can get close looks at them because of their how old they are as fossils. And we're feeling very lucky to have found a pair to take a look at with Lucy. All right, so finally, I'll just mention again that there was a bonus on the way out. We didn't just see 6 asteroids, we saw a 7th one in the main belt and got some data on that. And so in summary, we have the 5 Trojan encounters over a 6-year period, starting 6 years from now. 7 Trojan objects plus Donald Johanson. And I wanted to emphasize finally how we expect there to be quite low risk with this particular spacecraft in gathering the data when they get there. The reason for that, you may guess, is due to something that you always aim for as an engineer, and that is to try to use heritage as much as possible. And so the more legacy, the more previous operation, obviously successful operation, the more you've proven something and can reuse it, the more you can lower your risk for that particular, in this case, instrument. And so the 3 main instruments on Lucy, known as L. Ralph, L. Lori, and L. Tess, are actually all legacy instruments. You may remember the names Lori and Ralph from talking about the New Horizons spacecraft, which has gone to Pluto and now Arrokoth and is still out there sending back data. And so you just put an L in front of that for Lucy and take the same instrument, and that's L. Lori. I'm sorry, L, yeah, for Lori, yeah, for each of them. And so you get L. Lori and you get L. Ralph. The 3rd instrument over there on the right is a thermal emission spectrometer, a TES, fairly generic kind of instrument, but this particular one was flown over a dozen years ago on a Mars orbiter, and then flown again on OSIRIS-REx, where it's known as OTES. Same instrument now is LTES for Lucy. So we really have a lot of proven performance of the instruments that are headed out there. An artist concept of the spacecraft in the upper right there, showing the the antenna and the spacecraft bus in the middle, and the very large solar arrays, which you'll see in a minute, powering it. And then you see a blow up of the spacecraft instrument bus, showing in the 3 white boxes the 3 main instruments. And I'll just pick L. Ralph to start with over there. That is in fact 2 instruments. And if you look in the lower right hand or lower left hand corner there, you'll see MVIC for 2 of the bands. Those are in the visible to near infrared part of the spectrum. One of them is panchromatic, one of them is spectral bands broken up. And LISA is the other instrument that's part of LRALF, and that takes us out into the near infrared towards the mid. And then you see LORI, which is a high resolution reconnaissance imager, and you can see that it's down there in the visible band. And you see the third instrument, LTES, as you'd expect out in the thermal infrared, further towards the mid infrared region. And that's a nice spectral coverage by the 4 instruments actually on 3 different systems. All right, so let's see what the actual spacecraft looks like. Here it is in a test rig hanging in High Bay area. And you can see the width of it, it says is 51.8 feet. The solar panels aren't on it here. So in fact, that particular dimension as you're looking at it is only about 5 feet. Each of the solar panels, as you see, is about 24 feet, and you're going to see them in a minute. The depth of it from the outer end of the antenna feed there to the back is about 9 feet. And I wanted to point out to you some of the stuff on board, although we don't have time to go into the subsystems. You may have wondered how these orbits are made so precise and what kind of mid-course correction capability and so on they have. Well, they have an onboard rocket, and they have a very large mass of propellants on board here, making up almost half of the mass of the overall spacecraft at launch. The hydrazine and oxygen have been loaded. Well, actually, you know, this is, it's actually flying now. So they're on board. They'll be used up through the mission. I don't have any idea how long this will last. Cassini, you may remember, was finally put into the outer atmosphere of Saturn when it ran out of gas after, trying to remember now, what was it? I think 13 years of orbits through the Saturn moons and around Saturn. And so we'll just see how many of those repeat orbits Lucy can get through and still have the capability to adjust things and maybe further target every few years new asteroids in the L5 or L4 swarms. Note finally that there is a power available of 500 watts, not a whole lot, at the furthest encounter. And as I said, the orbit of Jupiter is where the aphelion, the furthest point from the sun of Lucy's elliptical orbit is. And so when you get out that far, Jupiter is 5 times as far away from the sun as the Earth is, roughly. And so to calculate the energy that it gets from the sun, you have to divide by 5 squared, or 25. So you only get about 4% of what solar energy we get here in a low Earth orbit out at Jupiter. And so despite that, that's the only power source for Lucy. And so Lucy sets a record with that. It is the furthest deep space spacecraft that will ever be flown and operated out there that won't have any nuclear power source on board to last through the years. And so total solar power, this particular picture of the spacecraft stack in the lab with these black triangles on the side, which you'll see in a minute, are the stowed or folded up solar panels. There's one on each side symmetrically. And here's yet another view of the prepared stack with the solar panels stowed on the side, ready to go into the payload fairing on top of the upper stage of the rocket. And so with that in mind, let's take a look at those solar panels. And I thought this was kind of a clever thing that Hal came up with to show us our favorite TIE fighter. Actually, it's not our favorite. We like the X-Wing, but at any rate, the TIE fighter, you may remember, and Darth Vader with his own. So you get a feel for the size of it, and that's about the same size as Lucy's solar panels. And so here you will get to see one of them in the lab during an opening test. And here are 3 technicians, the one on the right squatted down. The stowed solar panel is just above his head there. And we'll give you an animation here to show you that opening. And so you can see the solar panel as it, I won't say will open because they've already been opened on the real spacecraft in space. And just like an Oriental fan, there you see them opening up to their 24-foot diameter. It's silicon solar cells on top of a cloth backing with connections and enough ability to let a number of these cells go out from micrometeoroid impacts that they don't worry at all about having sufficient power for the very lengthy mission. And so you can see again now, as I repeat this, that kind of marionette or puppet-like holding affair up top there that's rotating all this stuff around. I think it's kind of a neat way to test the opening there in the lab. There's another view of it. All right, so I mentioned the record it will set for using solar panels only. Another, I guess you'd say almost record that it's going to set is how many target asteroids it's going to observe. In the history over decades of a variety of spacecraft visiting the main belt, we've so far only reached and studied 8 main belt asteroids, and Lucy in a single mission in just a few years is going to reach almost that many in one of these affordable discovery missions. And so finally, I thought I'd give you a status report here since Lucy has been launched, and it's now day 4, where day 3 ended at the 5:34 a.m. this morning. And so they're in their 4th day now. And I want to note that the first signal was received successfully back on one of NASA's DSN or Deep Space Network antennas less than an hour after liftoff. The spacecraft right now is traveling at 67,000 miles per hour. I don't know about you guys, but that's pretty fast. I think that's amazing. Does anybody know anything else that travels at that speed through space? Because you do, and I do, and the Earth does. And so as you remember from my trajectory there, the initial trajectory of the spacecraft, which it's now been put into, is co-orbiting with the Earth in a slightly different eccentricity. And so it's going at the same speed of Earth. And believe it or not, we're all going about 18 miles per second. And thank goodness for gravity. So that's what Lucy's traveling at on this initial one. Then it will go into its 2-year orbit and slow down as it gets further out. And then it'll go into its 6-year orbit. And so that's its speed. That's what it's doing right now. And then finally, I don't have anything more to say about this than what you may have read in the news. But when they opened those solar arrays, as you just saw, one of them latched properly and the other one didn't. There hasn't been enough information in what's mostly just the regular press, not NASA press releases, to say any more than at least I haven't seen anything that says any more than what I just said. I keep looking for NASA to have another press release. They have said, and the appropriate assistant administrator of NASA that's responsible has said that they anticipate that the mission will be fully successful, but he has also noted that they are investigating this issue right now. And I haven't seen anything more on that in the last couple days. So that's it, folks. I'm ready for questions.
Thank you, John. So I have a question. So once it gets into the 6-year/12-year cycle, you said that basically could go on indefinitely, right?
Yes. Yeah.
Okay. How long is NASA hoping that it'll last? Is there some official?
It's let's see, the contractors and their contracts require that there is defined a primary mission time. The primary mission time I mentioned is when they have just gotten to the furthest reach out there in the second full elliptical orbit, when they go past the L5 pair, and that's at 12 years. And so the primary mission lasts 12 years.
Okay,
and
one
then
cycle.
and then every 6 years they will return to Earth orbit and back out again and go through one swarm or the other. The solar panels have no reason to not continue to be providing sufficient electricity. The subsystems on board have nothing that limits them. And so even though Hal didn't give me, I asked him this question. He didn't give me any answer of what they expect. The party line is that the simulations show that this could go on for, thousands or tens of thousands of years. Obviously, we don't expect the missions or the instruments to last that long, but who knows?
Yeah.
I mean, we've now got Voyager 1 and 2 still out there doing things. What is it now? 25, 40, 41 years or so after launch. Things keep going. So we expect to get a lot of data for a long time. And I am very sure that the operational team and the team of researchers will be using the downtime as Lucy comes back in and goes back out for the next encounter to argue about and come up with candidates and then pick targets and things like that each time. But they only have picked the initial 6 so far.
What capability for collision avoidance does Lucy have as it moves through these swarms of asteroids?
Swarm is a term that, since we have a God's eye view of things here, we can kind of look at it that way. When you're in the middle of these swarms and in the denser main belt, when you're in the middle of that, from what I'm told, it's almost impossible to see with the naked eye any other object. So the idea that these things are getting close to bumping into each other, that's not to say that, as I said before, once in a while, an asteroid does have a collision with another asteroid. And we, guesstimate that that's once a year or so. They aren't close together. They aren't things that you can't easily fly between. It's not quite like, the space between, the particles in an atom, which is almost completely empty space, but it's pretty empty there. And there's no expectation that it will have any problem with collisions in terms of probabilities. And so the answer is there is no collision avoidance.
Okay, so the assumption then is that we know about everything that's in those asteroid swarms down to a size that would cause problems if it ran into Lucy.
No, I didn't say that. I'm sorry if that
Okay.
was what I
Okay.
thought I was saying. No, I'm saying that the density, that the spacing is such that they don't worry about it. The probability of hitting something is extremely low.
So it's just, for lack of better terms, it's really just being left to chance, that chance being
Yes.
very, very small.
Yeah, probability, right.
Jim.
But if you don't know about smaller asteroids in those belts, how do you know what the chances are?
It's a very good question. I'm afraid I'm not an expert on that.
Jim?
Okay.
It's pretty cold out there, I'd imagine. What is done in order to prevent the hydrazine from freezing in that you use some plutonium or something to keep things warm?
No, there isn't any nuclear material on board. I don't know, and I haven't, nobody's asked, and he didn't talk about it. As a matter of fact, he didn't talk at all about the subsystems. I had to go dig up the pictures that you saw, and I didn't look any further into it than that, I'm afraid. I could look into that, but I don't know the temperatures and I don't know the mechanism for keeping it warm enough.
I'm a chemist, so I'm going to look up the freezing point of hydrazine, which is well known, but I forget it. I used to work with it.
Okay.
I have a space heater they could borrow.
Yeah.
It's a big electric blanket, and we make it cool 500 watts.
A question not really related to the mission, but inspired by the discussion. In the talks about Pluto being demoted, I thought that one of the, I did not realize that there was stuff in the same orbital path as Jupiter. I thought one of the definitions that they came up with for a planet was that it had to have cleared its orbit.
Yeah, that's a very good.
That's the embarrassing question that always gets asked.
That's a good question. I didn't think about that. I said,
Does,
Are we gonna have to demote Jupiter now?
Jupiter's not a planet. Wow.
Yeah.
What are we gonna do?
But it's also not a dwarf, I don't think. So
Right.
we're in real trouble. They have to come up with a new name.
Is it just something that we conveniently ignore, John? Is that the best answer?
No, it isn't. And shame on me, because the question was asked the last time we talked to these guys, and there was a good answer for it. And maybe I'll remember it in a minute.
No problem. Again, it wasn't really related to the mission, but it was certainly inspired. I didn't realize that there was bits in there too. So I can look it up offline, but
I think the further, it's an IAU definition from 2006. And I think the answer was, and I think Hal answered this in one of our recent talks with him. I think the answer was something like, excuse me, the details of the definition don't just say has cleared its orbit. They refer to something that says dominates the space around it, something like that, which takes them off the hook from having the orbit be complete. Now you've reminded me of something else that I meant to say, and that is that Trojans are not just Jupiter. Trojans is a generic term for the L5 and L4 stable bodies in any two-body system. And so, as you can imagine, we've looked for them elsewhere, and we found that Mars has quite a few. And Earth actually has 2 that we've found so far. So stand by, there'll be more Trojans coming, but by no means does anything we found yet approach what is easy to be found.
maybe in the definition of clearing its orbit, maybe the Lagrange objects get an exception because it's impossible that it would clear those because it will never meet them.
Right.
Just a guess.
Yeah, Lagrange wasn't at the IAU meeting, so he didn't get a chance to. If he had made a point at that discussion, it would be known as the Lagrange point. Any other questions?
Yeah, John, the instruments that were flown, they were a robust design, as you said. Are these new instruments based on a robust design, or were they instruments that were, say, made, multiple ones made, and they had them on the shelf per se?
I don't know.
Because anytime, you have a robust design, but anytime you build a new one, there's always a chance that that robust design is got a flaw in it. Somebody thought or something right or something like that. So I was just curious.
Yeah.
Yeah. No, and version 1's always different than version 1.1, and but I don't know. if the contractors, after, building one to be the Hangar Queen, ended up having to build multiples in the event that one, was needed close to, I don't know. I don't know.
Another question.
Go for it. Yeah.
I mean, John, this is a multiple, almost decade mission. And, things change, people move on, people grow older, retire. What does NASA do to maintain the integrity of, the data systems and things of that nature? So, 30 years from now, somebody can still decode the data. I go back to this movie, The Martian, where you had to dig up this spacecraft, and then they got these guys who were all of a sudden in their 70s and 80s. They said, "Hey, you guys remember how we did this? And, turn this on." And so, so how does NASA do that? I mean, the pioneers pioneers have been out there, Voyagers have been out there.
Yeah.
The Voyagers have been out there. Yeah, we're still getting data from them, and it's like, does somebody still know how to decode it? It's like, having an 8-track player nowadays.
I still remember my DOS commands. It's fine.
Something like that. So, just
See
curious.
satellite run. It's fine.
I think the answer, let's see, first of all, the expertise the deep expertise for robotic spacecraft missions, as you must be aware, is shared between some government officials, which are probably much fewer, and many contractor engineers and scientists. And so the question really is about the knowledge base that exists in people. And it also is a question about how the data has been contracted to be documented and stored and updated and that sort of thing. And all I can tell you is that, and this is now John Conrad's opinion, this has nothing to do with NASA, but either they have spent an awful lot of money, and there's a very positive answer to your question, which I doubt, or the problems will be many if they have to revisit some very significant problems. Maybe Lucy's a good example of thinking about this, because they're going to have 6-year gaps between swarm fly-throughs over and over again. Like every half decade, they'll do something interesting. And so you picture 3 or 4 decades out, if the solar panels are working fine, there's no reason they shouldn't be. If there's still enough gas on board, it may be running out of gas. That's the thing that actually terminates the mission eventually. But assuming it doesn't, then there may be some things that come up where there's a glitch in the stabilization system, something or other. And can somebody get the prints out? They'd be digital. They'd be in memory somewhere. Can somebody I don't know. It's just that they're going to run into problems as the decades pass. And I don't think there's a very good answer to that, other than they'll work hard to dig it up.
I just remember, as a ham radio operator about 3 or 4 years ago, there was a gentleman that one of his, offshoot of ham radio was he would look for satellites. And he found a satellite that had gone right after its launch. It died, supposedly, to solar, to observe the sun or something like that. And it came back to life. It had reset itself and started transmitting. They thought it was dead. And then I remember reading they had to find the people that were ahead of the mission, because they had all
closed the mission.
They closed the mission. They did, they went different ways. Like, you guys remember how to even look at this data,
Wow.
what to do? And there was a scramble for that because this satellite was alive again. So it's just,
Yeah, it's timescales again. I think about the other side is the lucky data analyst. He only has to work 1 day every 6 years. So that's a pretty nice job.
Yeah.
Job security.
Right.
You get paid all year.
These super long missions now, it's like just like Todd was making a joke though. It's like, I can't remember, I can remember a few DOS commands from 20
Right.
years ago, but that's what we're looking at, the time scale of these missions.
Well, and just you figure a career might be 3 loops.
Yeah.
And then it's, you know, and that's a big career. It's just a whole,
And just how
it's a weird
technology
concept.
changes and data transmission changes and encoding and all this kind of stuff, somebody doesn't lose this.
cool. Any other questions from the online crew?
Let me just comment a minute on robotic spacecraft data. You guys are probably aware of this, or it'll make sense, I think, if you think about it, which is Cassini is a good example. Or let's go back, I mean, it just ended, what, 2 years ago? If you go back about 15 years, then it's Galileo, the Jupiter mission. The amount of data that's captured in those years of operation, in the case of Cassini, I mean 13 years of operation, there is such a treasure trove of data. And it's not NASA only, it's actually much more. Researchers at universities all around the world and astronomical institutions of various kinds, they spend decades going through the data that came from decades earlier and still learning things from it. And in the case of Lucy, I have to imagine that they have picked these targets very carefully and that they will have lots and lots of data on 6 targets of a variety of types purposely selected this way, and that they have lots and lots of researchers that are going to be digging through that for a very long time. And the question will be, especially if they don't come up with anything particularly exciting, let's say, the question may be, after a few years of the primary mission, is it really worth it to keep you know, the operational team on board and all the teams that it takes in order to identify candidates and pick the next targets and wait and capture the data? You know, they may decide not to have something well beyond the primary mission. I don't know. It's in the case of it's got to do with how much value you get out of the primary mission and if the opportunity will come back again. And now we look at this 6-year orbit that nicely goes through the swarms over and over again, and you know the opportunity will come back again. But it's, in this case, I imagine, got something to do with what they can afford to do and how much they are able to address the questions with the first data. That's my 2 cents anyway. These are good questions. I appreciate your bringing these up.
And again, anyone that's online, feel free to unmute yourself and jump in with a question. In fact, maybe what I'll do, let me switch things up here a little bit. We'll see how many of the online people are still with us here.
I have to stop and share. Oh, he does.
There you go.
14.
Cool. Any other questions?
Do you want me to stop sharing?
Yeah, go for it.
There you go.
All right. Again, last chance. Any final questions? Otherwise, again, John, as always, want to give you a big thanks.
Thank you all. Good to see you all.
Thank you for an excellent presentation.
And again, John, we'll look forward to the next one, and to the DAS members, look forward to seeing you at the next meeting or astronomy workshop or whatever other event we happen to see you at, either in person or over the screen. So again, keep your eye on the groups.io, and we'll see what happens next. And again, there are refreshments. For those that are here in person. I guess for those virtual, there may be refreshments, whatever you find in your own kitchen. Please enjoy. And Rob, so again, thanks again, everybody, and we'll see you all later.
All right.
Rob, what do I end this? I know there was something I had to do to save the video.